I have a second example here of the ratio test, and this is not normally how you're going to see the ratio test, but I want to make the point here that it's not out of the question. You might be given a series, and you might have to try to figure out what the pattern is and try to write it in summation form, basically writing expressions that will generate your series to be able to even apply the test. So notice this one here, and by the way, I'm not sure if you'd actually be given this because if you notice here, some of these fractions simplify, and if I simplify this, I don't think you're going to see the pattern. But anyway, if you notice here, that's 10 to the first, 10 to the second, 10 to the third, 10 to the fourth, and so on. Okay, the numerator, notice I'm multiplying by 2, and then by 3, and then by 4. Those are factorials on the top. Okay, so if I was going to write this using sigma notation, this would be a series that has factorials on top. We could probably go from 1 to infinity, or I suppose 0 to infinity, but I think in this case we're going to start with 1. We've got an n factorial in the numerator, and we've got powers of 10 in the denominator, and so that would be 10 to the n. And I would sub a few numbers in there and make sure it really generates that series. So just keep that in mind. If I give you a series of numbers, you may have to write the formula that would generate it first before you can apply some of these tests. All right? So just a reminder, the ratio test basically says we're going to act like this thing is a geometric series, and we're going to go really far out. And we're going to see as we go really far out, does it behave like a geometric series that is decreasing? In other words, that has a common ratio that is less than 1. Okay, so you're always going to take a term and divide it by the term that came before it. Okay, we call that the a sub n plus 1 term divided by the a sub n term. Okay, and that's getting a ratio between different terms. Remember that the ratio test technically checks for something called absolute convergence. So for example, alternating series, it's very often pretty easy to show if they converge or not. For a series that's positive, sometimes it's a little bit tougher. So absolute convergence tells you that even if your series was alternating, if you just looked at the positive terms, would the positive series converge? Okay? And if so, we say the series is absolutely convergent. If it doesn't, but the alternating series converges, we say it's conditionally convergent, just depending on whether or not we're looking at it being alternating or not. Anyway, so the big thing here is you're going to sub n plus 1 into your formula, basically, and you're going to divide by the nth term, which of course is really just going to be the original term here. Okay, so anyway, in this case, the absolute value is not going to be real important because n is always going to be positive. These values are always going to be positive. So that isn't always going to come into play a whole lot, but you really need to get in the habit of putting it in there just to make sure that you're using the definition correctly. Okay, so we're taking the limit as n approaches infinity of the ratio between the n plus 1 term and the nth term. So the n plus 1 term, and be careful here, if there's like an x or some other variable there, you're still just filling in for n. So it's going to be n plus 1 factorial over 10 to the n plus 1, okay? That's my n plus 1 term, okay? So it's kind of weird because we've got a fraction that's part of a fraction. We're going to be dividing by the nth term, which is just this, okay? So n factorial over 10 to the n, okay? And again, the absolute value here is not super important. Nothing here is going to be negative, so if you want to go ahead and take it out, you can. But for setup, I would include it there always. And more often than not, you're going to be giving an alternating series, and it does play a role there. Okay, this is an awful setup for a fraction. Okay, remember when you divide a fraction by a fraction, you multiply by the reciprocal. So you're really taking the n plus 1 term and you're multiplying by the reciprocal of the nth term is what's really happening here. Okay, so I'm going to take this guy here and just flip it, okay? And that'll give me a 10 to the n on top, and that'll give me an n factorial on the bottom, okay? And then we can kind of clean this up a little bit. I'm still going to take the limit of this thing. And what tends to happen, the ratio test tends to get used effectively, especially in cases where you have like powers, factorials, things where you can get a lot of cancellation, okay? And so notice here, again, you may want to rewrite this. Remember, if you do rewrite it and you haven't taken the limit yet, keep your limit notation in there. So the top of our fraction, we're going to have a 10 to the n. We're going to have a 10 to the n plus 1, okay? We're going to have an n plus 1 factorial, and we're going to have an n factorial, okay? So n of these 10s, we'll cancel n of these 10s. That'll leave us with 1 10 in the bottom of the fraction, okay? If you want, you could leave that as like 1/10, and you could factor the 1/10 out if you wanted, and just pull that out altogether. Not a terrible way to handle that, okay? Now, this is a factorial, okay? That's n plus 1 times n minus 1, all the way down to 2 to 1, okay? On the bottom here, that's n times n minus 1, all the way down to 2 times 1, okay? Fun thing about factorials is they create really nice cancellations in these problems. So everything is going to cancel all the way up through the nth term. We're going to just be left with just an n plus 1, not an n plus 1 factorial, literally just an n plus 1. Okay, so this whole statement is just going to simplify down to n plus 1, okay? And we're finding the limit of n plus 1 as n goes to infinity. Well, guess what? That's infinity plus 1, which is going to infinity. Taking a 10th of infinity still gives us infinity, okay? So this is going to approach infinity, which basically says this is a series that's getting bigger and bigger and bigger as we go farther out. If you're taking a term and dividing it by the term that came before it, you're going to get bigger and bigger ratios. So that is not less than 1, which means that this is a divergent series. By the way, if you flipped this, you would end up with a series, I believe, that possibly could be convergent. Well, anyway, I'm not going to go through that in this particular case, but sometimes if you flip it, you'll find out you get something that's convergent. Sometimes it still doesn't work, but anyway, something to think about. So that's how the ratio test works. Again, I can't stress enough, just be very careful. Make sure you're putting n plus 1 into both terms in your numerator, and then you're dividing by the original terms and simplifying the whole thing down. If the limit, don't forget the limit there, but if the limit of the ratio is less than 1, convergent. If the limit of the ratio is greater than 1, divergent. If it's equal to 1, it's inconclusive and you have to try something else. So hopefully that example is helpful in understanding how the ratio test works.